Okay, so calorimetry is a follow-up to specific heat. And before I can start talking about calorimetry at all, I have to remember the conservation of energy, which you've learned before, but I want to make sure we're all on the same page. So I've got a TED Ed because we know that I love TED Ed videos. So I want you to watch this. And it discusses.
Energy is not easy to define. Things have energy, but you can't hold a bushel of energy in your hands. You can see what it does, but you can't see it directly. There are different types of energy, but the differences between them are manifested only in how they make stuff behave. We do know that the total amount of all the different types of energy in the universe is always the same. Now, for chemists, two important types of energy are chemical potential energy and kinetic energy. Potential energy is energy waiting to happen. Think of a stretched rubber band. If you cut it, all that potential energy gets converted to kinetic energy, ow, which is registered by you as pain. Like a stretched rubber band, chemical bonds also store energy, and when those bonds are broken, that potential energy gets converted to other types of energy like heat or light, or gets used to make different bonds. Kinetic energy is the energy of motion. Now, molecules are always moving. They're not necessarily going somewhere, though they could be, but they are vibrating, stretching, bending, and/or spinning. Take methane, which is 4 hydrogens attached to a central carbon, as an example. Drawn on paper, it's just a still tetrahedron. But in real life, it's a jiggling mess. The kinetic energy of molecules is exactly the same type of energy as the energy you have when you're moving around, except that you can be still and molecules can't. If you suck the kinetic energy out of a group of molecules, they'll move less, but they'll never fully stop. Now, in any group of molecules, some will have more kinetic energy than others. And if we calculate the average kinetic energy of the group, we'd have a number mathematically related to temperature. So the more kinetic energy a group of molecules has, the higher its temperature. And that means that on a hot day, the molecules in the air around you are spinning, stretching, bending, and generally shooting around much faster than on a cold day. Now, hot and cold, by the way, are relative terms. They're always used to compare one thing to something else. So on that hot summer day, the air molecules have more kinetic energy than the molecules in your skin. So when those air molecules crash into you, they transfer some of their energy to the molecules in your skin, and you feel that as heat. On a cold day, the air molecules have less kinetic energy than the molecules in your skin, so when you crash into those air molecules, you actually transfer some of your kinetic energy to them, and you feel that as cold. You can trace the path of energy around you. Try it at your next cookout. You burn charcoal, and the release of that chemical potential energy shows up as extreme heat and light. The heat then makes the molecules of your burgers, your hot dogs, or your vegetables vibrate until their own bonds break and new chemical structures are formed. Too much heat and you have a charred mess. Just enough and you have dinner. Once in your body, the food molecules in your delicious or charred dinner get broken down, and the energy released is used to either keep you alive right now, or it's stored for later in different molecules. As night falls, the hot summer air cools, and the flow of energy into you slows. Then, as the air reaches your skin temperature, for the briefest of moments, the flow stops. And then it starts up again in the opposite direction as energy leaves the warmer surface of your skin to return to the universe around you. That energy neither created nor destroyed, but ever shape-shifting, the chameleon phoenix of our physical world.
Okay, so that's the idea of this conservation of energy. Okay, a couple things that I want to point out that he talked about. Energy cannot be created nor destroyed, right? It is ever changing, transferring, but it's not created nor destroyed. If one object loses heat, another object is going to gain heat. And heat always travels from hot to cold until thermal equilibrium is reached. There really is no such thing as cold in chemistry. There's only hot. So you don't let the cold air in through a window, you let the hot air out through the window. Okay? final temperature. And this is what calorimetry is based on as we start looking at it. Okay, the other thing that the conservation of energy says is the amount of heat lost by the hotter object equals the amount of heat gained by the colder object. So Q gained equals negative Q lost. In the case of calorimetry, it's going to be the water, the Q of the water, because that's what's gaining. And the Q of lost is going to be usually a metal object, but it really could be just about anything. So the heat of the water equals the negative heat of the metal. So here we go. Here's a basic calorimetry experiment. You've got your coffee cup calorimeter like we saw in the video. So what's going to happen is you're going to start out with a hot piece of metal and it's going to decrease in temperature. And then it's going to kind of level out when you place it in the cool water, okay? Hot metal gets placed in cold water and the temperature decreases and evens out. Now the cold water temperature is going to do the opposite. It's going to increase and then it's going to level out. Now I didn't make a mistake when I drew that. I meant to make the metal's temperature go down by a lot and the water's temperature raised by a little. And that's because the specific heat of the metal is so much lower than the specific heat of the water. The metal will change in temperature more easily than the water will. So you're going to see this over and over and over again in these calorimetry problems. Okay, so let's do one of these problems, okay? If we have a piece of copper metal, now it could be copper, it could be anything. I have some piece of metal and it's placed in 50 grams of water at 16 degrees Celsius. The copper and the water come to the same final temperature. There's that thermal equilibrium at 24 degrees Celsius. The specific heat of the copper is 0.385 joules per grams times degrees Celsius. It says to define as many variables as you can for the two substances. So we're going to find copper, all right, or the metal. And the reason I use the generic term metal is because it can be used over and over and over again. So we're going to have the M for the metal, the C for the metal, and the delta T for the metal. And then on the opposite end, we're going to do the water, all right? So you can have the M for the water, the C for the water, and the delta T for the water. So M of the metal, which would be the mass of the metal, it says I have oh, nope, sorry. That was for the water. We've got 50 grams of water. Okay, so 50 grams of water. C for water is easy. If you don't know it, you can look it up, but it's 4.18 joules per grams times degrees Celsius. And delta T for the water is T final minus T initial, right? So it's going to be 24.0 degrees Celsius minus the initial temperature of the water, which was 16, which is going to give us 8.0 degrees Celsius. And I'm maintaining the sig figs there. All right, so the mass of the metal is what I don't know. It doesn't tell me what the mass of the metal is. The C of the metal is 0.385 joules times degrees, grams times degrees Celsius. And the delta T of the metal, now watch this. You're going to have T final, 24 degrees Celsius, minus 86 degrees Celsius. So 24 minus 86. Now, if you are like me, you put everything into a calculator, and I just want to show you that 24 minus 86 does indeed give me a negative number. I want that negative number to stay, okay? So maintaining the sig figs, you get negative 62.0 degrees Celsius. So then it asks me, how much heat does the water gain? So I'm working here with the water amounts. I've got Q equal MC delta T for the water. So Q equals the mass of the water, that's 50, times 4.18 times 8. So the water gains 1672 joules, or if I want to maintain those sig figs, 1700 joules of heat is what the water gained. Now we know that that's the same as what the copper lost. So how much heat did the copper lose? It lost 1700 joules. Now, before you get yourself lost in negative signs, I would have kids argue with me and they'd say, well, that question says, how much did it lose? Well, it can't lose a negative amount. Well, whatever. It really doesn't matter whether you put that negative sign there or not, because at the end of the day, you guys should know that you're not going to get a negative mass. Okay. So Q lost is Q gained. All right, so then we move on to what is the mass of the copper. So we now know this amount. We know the Q amount, all right? It's negative 1700 joules. We just kind of found, oops, sorry. We just kind of found that out. So what is the mass of the copper? I'm going to say Q equals MC delta T. And I want to find the mass. So I'm going to divide by C and delta T on this side, divide by C and delta T on this side. And I'm going to get mass equals Q over C delta T. And I'll plug that into my calculator. I've got 1700. And I'm going to go ahead and use the negative sign just so it makes sense, divided by the C of the metal, which is 0.385, divided by delta T, which is negative 62 degrees Celsius. All right, and that does end up with a positive number. If you got yourself screwed up with the negative signs and you end up with a negative number there, guys, you cannot have a negative mass. All right, so 71 grams is my final mass. And that's it. That's how you do calorimetry problems. That's the basic steps that you'll take. You'll always have one object, another object, and then you'll have something missing. And I want to show you a little shortcut. If you are into shortcuts and you feel like maybe you're awesome at math or something like that, and you'd like to go ahead and do this on your own. When you do these problems, they're kind of the same thing over and over and over again. So you're always going to have Q, MC, delta T of the metal. So what you can do is, since Q of the water equals negative Q of the metal, right? You can really summarize that. And you can say, well, the mass of the water times the C of the water times the delta T of the water equals the mass of the metal times the C of the metal times the delta T of the metal. And this whole thing is negative.